Thank you very much. Hopefully you can hear me. And it's very nice to attend already Bernard's talk remotely. Special thanks to the organizers for agreeing to have me speak remotely. I apologize for not being there in person, and hopefully by having a live presentation and you can ask questions. And you would be happy to know that I'm not going to talk about multimodality and epic sounds. So that's something Bernard kindly covered. I actually want to tell you about something I am quite interested in recently, which is looking at video understanding out of the frame, which is quite a bit, a very good fit for this workshop. But of course, I'll present it from an egocentric perspective. So, this term, ego, is really not the greatest of terms. It really talks about one's self-esteem and self-importance. And hopefully egocentric vision isn't about the self-esteem of the researchers, but it's about this notion of trying to understand the wearer from their central reference point of view. By having this camera that's actually seeing what they see, following what they follow, and particularly the interest in studying objects, actions, interactions, and intentions. And as a result of this effort, most of what we talk about is a camera that is either head mounted or glass mounted, or the old days it used to be chest mounted until people realized it's not a good view of what people's interactions are. But really, and I actually created this using Veo, saying, can you create what an ego perspective is from a 360 perspective? You can't say a 360 video is not an egocentric video. For example, if you have a video like this, it is still an egocentric 360, and the red frame is actually Veo's prediction of what would be in a typical egocentric video compared to the 360. So the field of view isn't really what makes it ego or not ego. It is whether it is actually representing the intentions, actions of the camera wearer. So in this talk, I'm going to take you through a round of papers, a bit of motivation of why this is a topic that I've devoted all my career. And again, you become known if you're around in the community for a while. That's, if someone knows you, you've been around for a while, and I have been around for a while. And then I'll tell you about this video understanding out of the frame from 4 perspectives: point tracking, object tracking, gaze tracking, and hand tracking. This is the core, the majority of the talk, but I will give you a bit of a teaser on some of the work that's being conducted at Google DeepMind, not by myself, but some other colleagues, which is very much related to video understanding out the frame, and a bit of an outlook into some future directions before we conclude. And let's start by why ego. You're all in this room because hopefully you have some sort of a motivation of why ego matters. And my motivation is very much triggered in currently what humans currently do. We've lost the ability to use our hands because of how tied we are to this handheld device known currently as a mobile phone. It's not very mobile until you carry it. So it's really, the whole intention of something being mobile is that it can move on its own, and mobile phones really can't. And that's why we as humans really are tied to this. And apparently we want to remain connected. So there is a big, wave of devices, coming around. Some are already commercially available, but think of them very much as the very old, huge mobile phone, so that they're a step in the right direction. They tend to be multi-sensored to be able to be as efficient as possible. And some of the work you've heard is about how can we not have them record all these sensors at the same time. And if you think, oh, this is very far in the future, just like old mobile phones, there is always brave souls who start using the future well ahead of others. And of course, they are going to be made fun of because they're wearing as if they're carrying this huge old Nokia phone or whatever is the oldest thing that you could see. And my favorite one is this one. So yeah, people are already using these devices. Interestingly, if you ask Gemini to create an image of the future, what the future would look like as we all wear, these wearable devices, it cannot really imagine a future that's not as bulky as our current methodology. And interestingly, it still puts a phone in people's hands. So even these intelligent systems cannot imagine what this future would look like, and neither can yet we. But And Bernard introduced the Ego for the effort. So this is part of the data collection we've done in the UK for the Ego for the effort. So you can see what these egocentric videos show. They basically are following the person in their daily motion, recording both their daily activities, boring, interesting hobbies, as well as their chores. Okay, so let's talk about this video understanding out of the frame. I have spent the majority of my time working within the frames of those videos until in a collaboration with Oxford, we built from Epic Kitchens this. So we were able to lift these cameras to 3D. And if you know anything about 3D, you know that this is a very challenging task because of how dynamic these scenes are. So if you trust 3D now, you know that most of 3D works if you have a static scene. But really, if you have cupboards opening and drawers opening and the majority of your pixels actually moving, current methods do not work. So as part of a collaboration with VGG and Naval Labs, we were able to build epic fields to basically lift this scene from 2D to 3D. And honestly, I have been working with these videos for very long. But once I started seeing them in this 3D perspective, which I could imagine in my head, it became very natural to think, what can we do in this setting, as opposed to in the setting only within the frame? Because clearly, when someone looks away, they still know what's outside. And clearly, we are all able to understand what's happening in the scene without having to put an extra camera, just through reconstructing the understanding of the ego. So this is Epic Fields, which has been around for a while. I always tell people that they get confused. They go to Epic Kitchens, they don't see Epic Fields. I sometimes need to kind of create those links. But indeed, these are camera estimates for all our 100 hours of video from Epic Kitchens. And there is also a benchmark that allows you to trial dynamic novel view synthesis on 50 scenes. And these scenes are an average of 22 minutes long. Okay, so once we managed to lift our videos and actually know what's happening, where the camera is in the wild scene, to reconstruct the static part of the scene, what could we do with this knowledge? And the first thing we did was to look at point tracking. And this is a work we presented last WACV called Ego Points. For those not familiar with point tracking is the ability to track any point in the scene, just put a point and keep track of it. And these nice visualizations are typically created to showcase what the methods are tracking, because most of the motion in videos are motions horizontally. They create this, from top to bottom vertical rainbow, and so you're able to track these points as they are moving. And methods currently do really well. There are more recent methods. The ones we evaluated then was LocoTrack and CoTracker, and they seem to be doing quite good. Of course, as our expertise in ego, until we actually try them in an ego setup. And what happens is quite interesting. So the methods really think that these points are still in the scene but are occluded, because they are never trained to predict that the point is out of the field of view. So in this work, we identified the challenges that point trackers currently face in the dynamic egocentric video and propose a new benchmark with new metrics to showcase why current point trackers fail, along with a pipeline to generate some semi-real training data. And that's where the epic fields came to play. So first, we annotated some points in dynamic scenes. And these points are richer than typical points in datasets like Davis, because not only if a point is occluded, but whether it is dynamic or static in the scene. And then we created this benchmark where it's sparsely labeled in time, but you have these dashes that say whether a point is on a dynamic part of the scene, like the pan here, or in the static part of the scene, which is the solid lines. And we have these new benchmarks to actually evaluate what trackers can. Typically, trackers are evaluated like this. If the point is still in the scene, is it within the right threshold of the ground truth or not, which we refer to as in-view accuracy. Then we introduce this notion of out-of-view accuracy. Can a point tracker know that the point has left the field of view? And importantly, if it comes back again, can it re-ID the point? Similar to the sense of human re-ID. Can we re-ID that the point now is back in view? Importantly, after you allowed it to leave the scene. Compared to Tab-Vid-Davis, which is the most popular benchmark for point tracking, this has a lot more tracks, a lot of re-ID, much longer. It's sparsely labeled, but much longer. And we kind of showcase that current methods that seem to be improving a lot on this famous benchmark. They are not really improving a lot on the ego points, and worse, they don't do re-ID. So they can't perform this task of making the point leave and then come back. From here, we took the knowledge of the 3D points that we've reconstructed from the epic fields, and we equipped them with some dynamic moving objects to create synthetic sequences like this. So these contain points that actually go out of the track from the static scenes, as well as some dynamic objects. And notice that all point trackers are trained on synthetic scenes. That's why we call these semi-real. We produce quite a good improvement in re-ID, not where we want to be, but a step in that direction. Importantly, we're able to do stuff like this. So we're able to keep those points that are on the roll as well as the points in the scene. This is now a standard benchmark. So in ICCV, I believe Adam Harley and others are presenting this new point tracker called All Tracker, which is also now evaluated on ego points. So, one step in the right direction for people to pay attention to egocentric videos in standard tasks like point tracking. The next is, as we've built the scene, we wanted now to tell where objects are. And this work is called out of sight, not out of mind. What does that mean? We wanted to know where the objects are, even as they leave the field of view. So this is a little bit of a complicated visualization, but every time an object moves, we kind of have a neon point that tracks it in 3D, because we track the camera, we lift the objects, and we know where the object is in 3D. So in this case, the person is moving this, I don't know, this is a ball, and then puts in the sink. And while it is there, the model still keeps track of it. Also importantly, as the camera moves away. So this remains in the mind of the system even when it is out of the field of view and can be re-ID'd. We do that by lifting the objects using depth maps. Remember, the point cloud doesn't have any moving objects, but a monocular depth map has, but it's typically not metric. Even more modern metric approaches are not very good in training metric in ego because they're not trained on indoor scenes, on this type of indoor scenes. They're trained on like big rooms and outdoor scenes. So we used the static scene, which we built in epic fields, to see what part of the scene matches what is static in the scene, and accordingly to map this dynamic depth map, which is of this particular image, allowing us to lift the objects now from 2D to 3D. We do not have any ground truth. This is built on top of Epic Kitchen, so we don't have 3D knowledge of where the objects are. But we did evaluate if an object is seen from multiple views, what is the error in our lifting, which tends to be less than 5 centimeters. So we lift objects, we then match them by a combination of a knowledge of their 3D location and appearance, and then we keep them in the scene, allowing us to answer questions whether an object is in view or out of view, whether it is in view but hidden, so it should be here, but I can't see it, it's occluded. Also, whether it is within my reach, I don't need to move to have it, which are very critical and interesting questions for an egocentric assistive technology model. We really worked hard on this idea many, many times, and we submitted it in several rounds, and it kept getting rejected. Thankfully, this is presented now in 3D, but really it was on archive in early 2024. And every set of reviewers in all of our major conferences complained that we do not have ground truth. We can't do this because we don't have 3D ground truth. So we're not allowed to be able to do research without accurate ground truth, which is to a large extent infuriating. But usually, this is what happens when we do research. You're cornered by researchers, so you need to go and solve it. So we went ahead and collected recently unreleased HD Epic, which is a data set that is still collected in people's homes in the wild without any constraints. So it's not in the lab, very important, because what people can do in their homes is a lot more challenging than what you can collect in a lab setting. But we wanted to collect it with 3D ground truth. We worked with the ARIA team, so we have lots of ARIA devices. and we give people this backpack that has multiple area devices and instructions on how to record. We then ask them to start recording whenever they go into their kitchen and only stop recording as they go out. If you're familiar with Epic Kitchens, this is the same setting, but now using the more advanced multi-sensor devices. And then what mattered really is this level of detail. Hence, we call it highly detailed Epic. So HD is not about the quality of the sensor, but about the level of annotations. So after people collected the annotations, we looked at what recipes they cooked. We labeled the steps of every recipe, the prep, which is anything they did that was to prepare for the step. For example, if you wash the sweet potato, you need to have picked it up, and that's a relevant action to this step, but is not part of the step per se. We also ask people to weigh their ingredients, so we have ingredients weighed on camera and added on camera. And this is one level. So we didn't tell them what to cook. After they cooked, we had a recipe online, that's the closest one with the modifications. We have this prep step. So if they said chop tomato, then all the prep was retrieving the tomato from the storage, washing it, getting the knife, getting the chopping board. All that is labeled as relevant. In the first example here, cooking the pasta, you pick the kettle really 7 minutes earlier, and that is a relevant prep to that step. The next layer is this fine-grained annotation, which is much denser, along with audio in the same way we collected epic sounds, but it's much denser than the annotations we've had before. So if you look at Epic Kitchens, Eco4D, EO Extra4D, and HD Epic, you find that the number of words per sentence and sentences per minute and words per minute, all of that is increasing. But I told you that we started to collect it because we wanted 3D ground truth. And that's really, at least my main motivation for starting a new large-scale data set, which we wanted it to be, hopefully, every time we say that, the last one we collect. HD Epic is a validation data set, so it's highly annotated, but it's not supposed to be used for training solely. So for every object that's moving, we have a bounding box, a mask, and then every time an object is picked up and where it's put down. And this is done first in 2D, and these masks are manual. We start by SAM, but 50% of the time, the manual annotators would redo the mask because it's not good enough. So we have these annotators that only focus on one chunk of object movement. So they have the beginning of the object movement, the end of the object movement, and a bounding box at the start and at the end for every object that is moving across 41 hours of data and 9 kitchens. Because we have done out of sight, out of mind, we had a good trick to start our annotations and make them efficient. The object is typically static between being put down and picked up. So we have all our previous short tracks. We have the current track in time, which is at minute 4, but the closest one in 3D location. So this is the start of a track and the end of a previous track. So at the same location, there is this one, it has a name. So a manual annotation would say, yes, that is correct. But by really ordering everything by how far it is in 3D, made these annotations, which would have been impossible to do efficiently, really extremely efficient. Huge kudos to the researchers who've worked on creating these interfaces. So everything was manually collected. So hopefully now we have ground truth. And we actually lifted it to 3D. In addition to the point clouds that come with the area glasses, we worked with a sketch artist that built surfaces of the scene and reconstructed all the kitchens. So you have all the drawers, cupboards, etc. And now we have the full ground truth for all the objects that are moving in addition to the masks, which we don't show here. You're asking me, what are you doing now to track these objects in 3D? Hang on. We already released the dataset, so we are in competition with all of you to try to do out of sight, not out of mind, but hopefully we have the follow-up to this work soon. Okay. Hopefully I'm doing okay with time. The next bit is also related to HD Epic, but it's about gaze fixations. It's about the fact that people look at objects before picking them up. And because we now operate in 3D, we can do this exercise of figuring when someone looks at the object well before picking it up, but also when do they look at the location they will put it down, the empty location, like this. So already the person from this distance is gazing at the exact location they're picking up the glass, well, I think it's a cup or a glass from. So they're priming the pickup. But what was really interesting is this, is how far ahead in time are they priming the location, the empty location they're going to put the object at. And this data really confirms data that was only collected in the lab about gaze priming, along with an interesting long tail we're still analyzing. The data is out. You can use all of it, including the gaze priming, which we released only recently, along with the VQA. I'm going to pause a little bit because VGG Oxford have created a fantastic interface to allow you to search through HD Epic using it through a project they call WISE. So you can go and search what the dataset contains in actions, objects, etc. Lost in video understanding out of the frame is a notion of hand tracking. So recently, you're probably aware of this, that thanks to the ARIA devices and lots of interesting research, this is work, this CVPR from Berkeley, we're able to reconstruct the full body of the human from an egocentric perspective. So these are models trained from EgoXO4D and Nymeria, and then evaluated, and we actually run them. If you see the HD Epic visualizations, all our humans are created using the EgoAllo model. In this work, we wanted to actually solve one problem we have in hand forecasting. In egocentric, hand forecasting is only done when the hand is in view. So if you want to track the hand, you assume the hand is already in view, and then you predict where the hand is touching, which is almost always too late. We wanted to actually track the hand even when the hand is out of view and into the future, simply because we can imagine where the hand is through imagining the rest of the body. And this is a work available on arXiv led by Masashi Hatano that was visiting our lab from Kia University in collaboration with Jifan in the lab. It's called the invisible ego hand. So during the observation period, you condition the camera estimation, the 2D hand and the image features, but the hand might not be in view. But this is trained through the EgoAllo predictions to know where the object is even when it's out of view. And then in the future, you can predict where the hand will be. So we predict the full joints of the body, including the hand, as well as the 3D to 2D projection that should match if the hand is in view or not in view, allowing us to predict the hand even when it is out of the field of view. And the paper comes with a very interesting ablation of how well we perform comparing to prior work when the hand is in view. This is what prior work has tried until now. But importantly, how to predict the hand when it's out of view, which has not been attempted before. And it comes with an interesting ablation with the various components of the paper. And of course, visualizations are the best thing. So you can see the forecasting in 3D even when the hand is out of view, as well as the forecasting of the hand in the pose when in view. Okay, this is the thrust of what I wanted to present to you mostly, but I wanted to tease some of the work that's being done at Google. And the first is called The Wizard of Oz at the Sphere. So The Wizard of Oz is a movie that was done in 1939, and it has lots of iconic characters. And recently, Google have been able to present it through super resolution, outpainting, but my favorite part, once you basically look out of the image, you are bringing characters back in view, and you need to make them act in the same performance they would be acting. So we all know how to do super resolution nowadays. You can train a model to do super resolution. But outpainting is really tricky because this movie comes with certain plot parts. Dorothy, for those who are familiar with the movie, only wears these red shoes at a part of the movie. So you have to actually train the model to understand where are you in the plot. And importantly, once you look outside, you are expanding the field of view. You are going to bring characters in view, and you have to make them act in a manner that connects the dots. Very much out of sight, not out of mind, but also for characters. I'm going to skip this in the interest of time. If you're interested, look at the behind the curtain at Google, and you know that this is done through a fine-tuning of a VO model. The other one, probably that became more familiar, at least in the vision community, is Genie 3, which is a model that actually takes actions from humans and can consistently predict the status of the world in both synthetic and realistic environments. And my favorite one clearly is the one on the top right, where you can look back at what you painted and it's exactly preserving that location. As we all know, the number of actions in these models is still limited, but this is still quite impressive. And what's most impressive, it's known as the new frontier of world models. I'm not going to argue about what's a world model, but it starts with a text prompt and could take a starting image and video and generates an interactive world at 24 FPS. And what's important is that things remain consistent for several minutes, and this consistency is an emerging capability, i.e., there is no 3D world reconstructed. This is an emerging capability of training a model, which raises questions about how out of the view doesn't need to happen in a strict metric 3D setting. I know you're all interested in ego and the future of ego. If you haven't seen this paper, I would encourage you to give it a look and let us know what you think. We wrote this survey in a slightly different manner. It's published at ICCV, and we tried to envisage what the ambitious future would look like for egocentric vision. We imagined stories of people in the future, and we wanted to kind of draw what they look like. So we worked with a sketch artist that drew our envisaged future of what the capabilities of these ego settings could do, not only at home, but also in settings like with a designer, with police, through social interactions. After we drew this future, we went and related it to the current state of the art. We wanted to be really not tied to the current state of the art in imagining the future. And thus we allow to show the gap between such a future and current technology, both in seminal works, state-of-the-art data sets, and the gaps to go for the future. At least you can read the first part, which is the interesting stories, and tell us if this is a future you would like to live in or we're going in the wrong direction. I always get the pleasure to come and present these works, but this is a work of a huge team that has worked over the years, including particularly the past year and a half to produce HD Epic, and I'm always very, very grateful for their efforts. And I'm thankful for your time, having chosen to listen to me rather than be on the beach in Hawaii. So hopefully this was useful. Thank you very much.
Thanks to Dima again. So we have sufficient time for a few questions. Any questions from the audience? Okay, I'll start with a question. So yeah, in your kitchen scenario, it's great. So it creates quite a lot of challenging scenarios. So I'm always curious about, so have you ever considered what if the form of the object changes? For example, when you break an egg into a piece of hard part and soft liquid and chop a carrot in different pieces, or when you are cooking, when the heat comes in, the color and appearance of the food are changing, anything like this.
Sorry, what's the question?
Yeah, I mean, when the form of the object of the food is changing, like the color appearance, or when you chop a carrot into different pieces or break an egg into something. So have you considered this, and would the model
we have multiple ways of addressing this. We do have this adding. So adding ingredients to recipes is labeled. But if you talk about the 3D tracking of objects, we have to stop tracking when the object breaks into pieces and assume it's a new track because we don't know what to do with it. So this link between an object and then 10 objects that emerge out of it is currently not labeled, currently underexplored. And I had lots of discussions at some point with Professor Matas on object tracking. And, it's very hard to know what you're tracking if it changes form. And perhaps point tracking is one way to address this, hence my interest recently in point tracking.
Yeah, Yeah, exactly. Like you mentioned, the point tracking. Have you observed that when the object is continuously, the whole changing process, you can observe that when doing the point tracking. Is there any
So
possibility that
yeah,
the point still tracked?
yeah. So unfortunately, because point trackers are trained on synthetic scenes, and
Okay.
synthetic scenes currently don't have deformable objects because synthesizers emerge primarily from gaming and they don't have DOEs and things like this. So they only have, unfortunately, people exploding, which is not what we want to track. So our reliance on synthetic data and point tracking will stop us from being able to perform the task, but also it's impossible to label points in real data. So, an interesting question.
Thank you. Any other questions from the audience? Check online if anyone. Okay, any questions? Yeah.
Thank you for a really cool presentation, Dima. Had a question on the point tracking work. So you had the ability to re-identify objects. How does that work if you, for example, are like moving an object, but it's not in your field of view, like you picked up a kettle and it's in your right hand, but you're looking over to the left of the kitchen. Are you still able to re-identify even when those objects are moving when they're out of view?
Yes, we are. The interesting thing is, do you want the models to also know where the object is when out of view, which we don't expect? We expect the point tracker to just to say the object has left the field of view, and then to say the object has entered the field of view and it has been re-ID'd. So currently out of view accuracy is just, is it out, but not where is it out, right? How far? And then once it comes back, it kind of tries to match it to the original point trackers. So luckily the point trackers always rely on this static memory of the first point. They don't update in the way current point trackers work. They still have this knowledge of the original point, unlike VOS like type of memory where things get updated. So it does work, but it still is it's possible. It just needs a lot more training for that particular scenario. And if I can follow that up to say, we are asking now the question of whether this is a tracking task or a correspondence task. And I think this is more correspondence than tracking.
We have one more question from the audience. You can call.
Hi, Dima. Thanks for a great talk. I have a quick question about the current video VLM model in the world, including like Gemini, for example. And what do you think of the current state-of-the-art video VLM model's performance, and what should be the direction of the research for them in respect with respect to your kind of egocentric vision's perspective? Thank you.
Yeah. What we wanted to show in some of the VQA we set in HD Epic is that short-term video understanding is not solved. So everybody tells you, oh, we're very good at short clips. The only problem we're facing in VLMs is long-term. That's not correct. So we've set this VQA that asks stuff like Gemini, and Gemini does a lot better than the other models, but asks it, it shows it a video of someone washing a plate, and then asks it, there are 4 descriptions of how people wash plates. Which one exactly is this one, right? And maybe the person here is looking at the plate, turning it around and washing the back and then flipping it, right? And then the other examples, it's not saying that. And models fail badly. So short term is still a problem when you want to really understand manner, which is very underexplored. And perhaps we showed that through that detailed understanding. I am very much interested in the 3D knowledge because I think ego is very hard to do in the frame. And if these models cannot reason about out of the frame, I think they struggle, and they can't currently because they've not been fine-tuned for such a task. Of course, everybody else will tell you long-term video is the task of the future. There is a lot of work in that. I think long-term video will be solved. I think detailed video understanding and understanding the sense of what happens out of the field of view remains very far-fetched. And models are not trying to do that at the moment. Interestingly, as we have seen, diffusion models are capable of doing this, while perception models are not. And I'm sure as you walk around ICCV, you see lots of people either analyzing, comparing, or questioning how can we merge understanding and generation, because they seem to be able to understand different parts of the world. And that I don't think there is a clear answer for.
Follow-up question?
Yeah.
Can I have one more follow-up question for that? It's
Sure.
the things that you mentioned, what the vision model can achieve, but not the perception model can't. Can you explain more about those things?
So currently questions about 3D, if you ask Gemini, like how far is this behind you? And I'm not ask it about the dimension of an object, because it had seen all these objects in the world mentioned on websites with their dimensions. That's easy. That's not 3D. 3D is when you give it a video like you, and then you turn around and try to understand, where is this object relative to me now? And it can't do this. While stuff like Genie currently can do persistent stuff through a diffusion-based approach. So it's interesting that current models trained with a language at its core, but there is a lot of spatial stuff people talking around. I'm really talking about understanding the world out of the inside of the frame, because there is a lot of understanding of spatial inside, and these models are improving. I am talking about the world outside, while diffusion is capable of now producing, you look right, and then it generates a video, and you come back and it's consistent. If you give the same type of input to Gemini or other VLMs and say, okay, I'm looking at the right, that's what's happening. I look back, what do I see? They don't give you the right answer consistently. Again, they haven't been trained for this task. So is it a matter of data, or is it a matter of model capabilities? Unfortunately, very few people have access to large-scale training of both perception and diffusion models. But I believe the community is waiting for that clear signal of, is it data, is it task, or is it actual diffusion versus RL versus perception.
Thank you.
Thank you for the time. Probably we'll stop the question here. But yeah, thank you very much again to Dima.